All right, sorry about that. How is everybody doing today? How was your weekend? Mine was fine. I did stuff good. All right, let's get started. So, before we head on, you should have had an opportunity by now to look at the project. Any questions on the project? Yes. Yeah. Yeah, sorry, I used inconsistent. In my mind, I called that the pregnancy term factor. Would you shoot me an email and I'll fix that on the webpage? Yes, sir. Okay, so here's the deal. For this assignment, this Wednesday, you have the design document due. You will submit that only through Blackboard. That will be the algorithm expressed as input, output, decide, stuff like that. The following week, you will submit it to AutoGrader and Blackboard. I just noticed when I was looking at the project page that I forgot to include that, so I will fix that as well. Anyway, sadly I closed the page here. So, but anyway, you'll do it both. Yeah. Yep. Not in your design document. It is the number of days out of a month, so it will be an integer. You do not have to do input validation. So people range from what? No, in the real world, not in the assignment. People range from, at best, imperfect to at most suck, right? So when you write computer programs, you have to anticipate that people will be imperfect or suck, or will put bad values in. So sometimes we're going to have you in this class check that the values people are inputting are reasonable. We're not doing that for this assignment. The reason is this assignment is challenging enough without that. The other reason is in the real world, when you're doing these types of surveys and you're enrolling people, you're dealing with people who are professionals. And most of the time, they're not entering things by text. Most of the time, they have like an iPad app or something that has like a list of values. So for this, we're going to pretend that they never make mistakes because they're only working with a limited range of values. Okay? So when people input things, you don't have to check and make sure that they make sense. You can just blindly trust that they're in the range that I told you they would be in the project. Other questions? Yeah? Uh-huh. Yep. I should have fixed that. When did you do that? Ooh, that's not good. Hang on a sec. All right, so we're on CS class, and you should have permissions. So if you do ~clay/enroll.exe, you should get this that pops up and runs. If you don't, let me know. Once you're logged in, you should be able to do that. Okay? If it doesn't work, let me know. Yeah? Nope. Nope. There are interviewers who go out and interview pregnant women and they try to recruit them. Some of the women they recruit might be in their first trimester or their third. They will have an estimate of the number of days. They will not all be there. Other questions? All right, so for this assignment, I spent like all weekend doing this, so I can't help but show it off. We will be using the AutoGrader. What? I just went through, I'm not going to do this. I'll do it next class. Okay, I'll show you how it works. So I thought I had left the window open, and apparently I did not. So no point in watching you all watch me log in again. Bad clay, no biscuit. Okay. All right, other questions? So when it comes time to submit, you'll submit through Blackboard, you'll submit through AutoGrader, and I'll talk about that next class. So, okay. Any other questions, comments, concerns? Yes, criticisms? I don't know if you'll be able to get your outlines back with feedback from the TAs. We will do our best, but the TAs are students like you, and they may not. Like I said, we'll do our best. The point for me is not to make sure you do everything correctly. The point for assigning the design documents is to make sure that you do thinking a week ahead of time so that you don't leave everything till the very last minute and try and do it the night before. It is me forcing you to work early and giving you an opportunity to get like points, because we're relatively lenient on grading those. So, other questions? And we're still working on the other homework. Homework 2 is graded if you submitted it through AutoGrader. Isn't that good? You can go and look online and see what it looks like. Okay. Last time we finished up talking about different data types, right? And we talked about a bunch of different numeric data types. Why do we have different numeric data types? You made eye contact. You made a huge mistake. You have to answer the question now. Right, sometimes we want decimals, sometimes we don't. Sometimes we know we're working with only positive integers, so we use unsigned. Sometimes we know that we're working with integers that cover a whole range. So let me ask you a question. How do you decide which one to use? How do you decide? Yeah. That is an excellent answer. And that is the non-obvious answer. So he said, based on what we want as the output, we choose our data type. It is not clear, the standard answer is, depending on what we're getting in as an input and working with, we choose our data type. But here's the deal. Sometimes if you choose a data type to hold input, like unsigned int, can unsigned int go below 0? What happens if your unsigned int is going to be used in an equation that might go below 0? It's going to be bad, right? It won't actually have an error. It'll wrap around, and you'll get the wrong value. Okay? So what you want to do is you want to look at what your output type is. If your output type is going to be an integer, you want to use a long or an int. Okay? If your output type is not going to have a sign, if it's going to be between 0 and something, and no part of your calculation has anything that has a sign, you can use unsigned. But only if no part of your calculation has. Okay. If you're doing floating point values, what do you use? You know, I just want to comment, it's amazingly how quick I can train a class not to look at me by just calling on people who make eye contact, and then every time I ask a question, everybody's like, yeah. Okay. So you don't have to answer all the questions. I owe you some candy, but you don't have to answer all the questions. So what do we use? What are our options for decimal values? Yeah. Double, and what else? Yeah, like long double. So, okay. Yes, sir. No, float is the equivalent of short double. All right. In general, as a rule of thumb, use double. Okay? Use double. Throughout the semester up to now, I have used float, and the reason I've used float is because when you're new to this, float makes sense, right? Floating point number float. Double isn't clear that it's a decimal thing. But double is better. It has enough accuracy in its decimal places that it won't get you into problems. Float can get you into problems, as we might see. Okay. There's just not enough, it doesn't carry enough decimal places that if you have a big number, that the decimal places can still be accurate. All right. Everybody good on that? All right, so there's one other type of thing I would like to show you. All right, is that big enough? Should I make it a little bigger? Don't need this menu. I wish it would not be there. Okay. So let me do a little math equation here. Let's say we have a character. Its name is x, and we set its value to 9. And we have a character, and it's named y, and we set its value to 7. And let's have an integer, and we say z equals x plus y, and we see out z What is this going to output? Yes, sir. Nope. Yeah? Nope. Yes, sir. Nope. X plus Y? Nope. Yes? No, it will not output 0. Any other guesses? Yes, sir. So the question is, will it output a character? Nope. It's going to output a number. The number will be an integer. Yeah. 16. That's the obvious answer. No. You obviously don't know. So let's run an experiment and find out, right? So when we run this, what's going to happen is we're going to get a warning. The compiler is going to give us a warning. Does a warning keep your code from compiling and running? It does not. So when we compile this, we say g++ charint.cc-o charint. So we're compiling the program, outputting it in charint. Oh, didn't give me a warning here. When I compiled this on my other machine in the office, it gave me a warning. Okay. So let's run this and see what the output is. Ready? 112. Why did this happen? Right? This is insane, isn't it? I love it. It's in 7. 9 plus 7 is 112 if you do it this way. Yes, sir. Okay, yes. So here is the thing. Everything in the computer consists of ones and zeros, and it's just how you interpret those ones and zeros, right? Is there a set of ones and zeros for the character 9? Not the number 9, the character 9. There is, right? But it doesn't happen to have the value 9. It has a code number, and the code number represents the character 9, and there's also a code number that represents the character 7. So what I can do is if I see out these things, and we actually look at the values inside, we're going to find out what their actual code numbers are. Okay? It turns out the code number when you're talking about a character that represents the number 9 is 57, and the code number that represents 7 is 55. When you try to add these characters together, you don't get like 9 plus 7, you get 57 plus 55. The moral of the story is, don't add characters together, okay? I want you to understand the difference. Even though, in this case, the characters had numeral things in there, it doesn't work like you think. It does not work like you think. Okay. Yeah? Yeah? So I will show you where these code numbers come from, briefly, very briefly. You don't need to know this. I'm just going to show you because it's like, I don't know, interesting. I think it's interesting. I'm such a loser, aren't I? So there's something called the ASCII code, and if we go someplace, you can look it up. Hopefully this one is like a safe link. So these are all the characters, and you can see they have like what they have is an ASCII value, and this ASCII value represents a thing. So if we look over here, we see ASCII value for 7 was 55, ASCII value for 9 is 57. So for letters, there's like this magic code lookup table that translates these code numbers into letters behind the scenes. It's called ASCII. That's all you have to know. You don't have to know any of the values, okay? Just that, when you try to work with characters, if you try to do addition or anything like that, you're actually working with the code number, not the actual character. All right? We go with that? And we can do weird stuff with this now if we want. Like I use 7 and 9 just because that is maximally confusing. I can actually put like a space in there and an @ sign, you know, or something like that. And then we can compile those, we can run them, and the sum of a space and an @ sign is 96. Right? Yes? yes, if you wanted it to be 9 plus 7, you would not ever declare them as characters, right? You would want to declare them as integers, and then they would be added correctly. Does that make sense? So. All right, everybody kind of see this? This is, I don't know if it's super important to know, but it can get you in trouble. Yeah? You should use characters. We'll use them later in this. Well, actually, we use them for this project. Because when people are entering things, they'll answer, I have a yes-no question. Can I put Y or N? That would be a character. Later in the semester, we'll be writing a program that has a menu. And it'll be like, please select a letter from the menu. And you push the letter from the menu. And that will be. So anytime you have one single printable thing. Okay? And those printable things can include digits. So don't get confused when I put this kind of question on the exam, which I probably will do. So that you can prove to me that you know the difference between characters and integers. All right. Happy? Who's happy? Okay, so. All right, so now we're going to start talking about output, because when we have a program, we want it to do stuff that we can understand, right? There's not always a lot of sense having a program that does things that you can't see. So here is what cout looks like. Sorry, I was writing code all weekend in a different programming language that used pound signs as comments. So if I type a lot of pound signs today, all right, everybody remember this notation when we talked about it before? What do these square brackets mean? Yes? That things are side or optional. So we have cout, and then optionally we have, and sorry, the cursor there is right there. It makes it look like I'm doing something I'm not. But we have cout, and then optionally you can have angle brackets and a parameter. And the star means, nope, it does. You're absolutely right. Star means end comment. But in the notation that we're using, it means 0 or more, okay? So when you have cout, you can have cout. That's it. If you want to have that, it doesn't do anything. It's like the null, don't do anything cout statement. Or you can have cout followed by angle, and some parameter, okay? As we'll see, a parameter can be defined as a couple of things. But I'm just going to cheat here and say that it is either a variable or a terminal or some sort of control, because we'll see there's some control things that you can insert in there. Okay? All right. Later we'll see that. All right, so let's output some stuff. How's that sound? Int x equals 5, y equals 7, z equals 0. Sorry. Cout x, y, z. What will this output? Yes, sir. 570? Yeah, are you being ambiguous or am I being ambiguous? Uh-huh. All right, if we run this, it will output 570. It will look like 570. Something went wrong. What went wrong? Yeah. We didn't put any indels. We did not do anything to separate these variables. Okay, what will this print out? You already answered. Someone else. Yeah. 5 space 7 space 0 and then the command prompt will actually be on the next line down. Sorry, I was aiming for your back. Okay, that's her. So let's try this one just to show what I'm talking about. Five space 7 space 0. Okay? The way I think about cout is cout is the screen, right? And these little angle brackets, these double angle brackets are like the funnel. And things get shoved through the funnel and they appear on the screen. And they appear on the screen in the order they are shoved in there. Right? So the first thing that's shoved in there is X. When you see X, what does the computer do? It says, there's a box somewhere named X. I will go in there, look what value is in there, and replace that thing with the value in type. And so, oh, that's 5. I'll output it. What is this double quote thing here? It's just a space, right? It's part of a string, which we haven't talked about. Cout Y, space, cout Z, end line. And the line goes to the next line. Pretty straightforward. All right, what happens if I throw some extra end lines in here? What's this going to do? It's just inline. It shouldn't be that confusing. Yep. It will. All right, so here's what happens. Oops, did I compile it? Everything goes in the order that it was put in, right? So, cout reading from left to right. First thing that happens, there's an end line, which is this right here, right? It goes right down to the next line, even though it didn't print anything out. Then it prints out X and a space. Then it prints out an end line. So it prints out X and a space. If I highlight it, you can actually see that space. See where it turns blue there? And then that right there is the end line because it goes to the next line. Then it prints out 7, a space 0, and an end line. Everything goes in which the order is received. That's pretty straightforward, right? Who's happy with that? Who has any questions about that? 17-second rule is in effect. 16, 15, 2, 1, 0. Okay, good job. Yes, you can use reserved words as the title of a file name. That's fine. You just can't use them as variable names or function names when we get to that. So. All right. 1 minute break and play, stand up, stretch, go. All right, welcome back. While you were gone on that refreshing, invigorating break, I turned up the mic a little bit. Hang on, is it too loud back there? Is that better? Is that good? I had to turn it up for the recording level in the video. Okay, so while you were gone, I added some code to our sample program, just so that we could do some other even funner stuff. And here's what I added. I added an int p, which has the value 123,987. I added a double floating point number, q, which is 18.73. I added the character named r, which has a pound sign. And then I output each one of these things, p, q, and r, with an end line after them. And then also I output this thing that said this is a string literal. A string literal is how you output like a message that is more than one character. Notice that a character has single quotes around it. Notice that a string has double quotes. Okay? So if you want to output like a whole long message all at once, like you've seen when you did I did my homework program, you put double quotes around it. Right? Yes, sir? What would happen if you didn't put the quotes around the If we didn't put around this? Well, I will show you. So first, the question is what happens if we didn't, it compiles cleanly right now. If we didn't have the quotes around the character, if we just put that in there, it would not compile. It would be an error because it doesn't understand how to assign a pound sign to a character because you need to put single quotes around it to make a character literal. Okay? So if you see this error right here, expected expression. It was looking for an expression, but it got a literal that didn't have quotes around it. Okay, so what is this going to output when we run it? What's our algorithm? What's this thing doing? Yeah. Yeah, so it's going to output all the stuff we had before, X, Y, and Z, right? And then it's going to output these new values, P, Q, R, this is string. How are all these things going to be formatted? Where are they going to appear on the screen? Yeah. New lines, are they going to be on the right side of the screen, the left, and the center? All on the right side. So, would you like a Yeah, my other left. Okay, so let's make sure that I'm right about this. All right, so here are the 570 we output before. I'm going to put a couple more end lines in just to separate those. Okay, so here are the things that we output before, and here are these new variables that we output. Okay, and you know what I think? I think that's kind of ugly, isn't it? Like if you were reading along with a whole bunch of stuff, like this 18.73 should probably be lined up differently, shouldn't it? To make it stand out a little more. So what I'm going to show you is how you can format your output. What we're talking about is input formatting. Okay? In order to do input formatting, we have to add something up here to our header. IOStream is the library of code that we're using for output. If we include something else by doing pound include IOmanip, that does input and output manipulation, what will let us do formatting. Okay? And the formatting that we're able to do has a couple of things. One thing that we can do is we can use something that's called set width. Oops. And let me just go in here and I'm going to put some set widths inside each one of these so that we can format everything nicely. What set width does is it says when you print the next thing to be shoved into cout, so this set width says when you print this next thing here, P, print it in a certain number of spaces. So let's put this as 5. Instead of printing it in one space or however many spaces, print it as 5. So we'll use 5s all throughout here. Okay? We're going to format this to output as print out as 5. So compile. When we run it, here's what we see, right? Here's our old output. Now here, we're printing things inside 5 spaces. Can you see a difference? Who can see a difference? What difference do you see? You raise your hand first. Which one is more spaced out and look nicer? Okay, the only thing that's different this time from last time is now there are some spaces in front of the pound sign. What we said in our code is we said, for P, print it in 5 spaces wide. How many digits is P? 6. Can you print something 6 spaces wide inside 5 spaces? No. How many spaces is Q? 5. If you print something that's 5 characters inside 5 spaces, does it just fit exactly? It does, so there's no difference. How many spaces does this pound sign take up? 1. It doesn't take up the quotes. So when we print it inside 5 spaces, we get 4 spaces to the left first. So if we count these by highlighting them, let's see, 2, 3. Well, there's 4 there. I can't get them. So there's 4 and a fifth. How long is this string literal? Long, right? I don't even care how long it is. It's long, but it's longer than 5, so it all overflows. So that didn't really help much. But we can do something like this. We can make them all 25. What's going to happen now? Yeah, everything will get shifted over to make space. Let me clear, compile. We compiled completely. We run it. And now everything is shifted over and it's kind of lined up on the right side. So this is one way that you can format your output. Okay? All right, so that's pretty basic. That's useful. You don't need it for this program, but you'll need it later in the semester. Okay? Any questions so far? Is all this stuff pretty easy? Do y'all think it's pretty easy? Good, because this is what I want. I want you to know the easy stuff well so that the hard stuff later doesn't break your will to live. All right, let me create a new program here. All right, so we are going to load up this new thing called set precision. I'm going to include the header IO manip, which we were using last time. And we're going to do some floating point math. So let's get a double value pi. Who wants to tell me what pi is? Because you all yelled at me last time for doing it wrong. Someone raise their hand. No one knows what pi is. Yes, pi. Is that good enough for everybody? That's what I had last time, and I thought, and you yelled at me. So, all right. All right, so we have pi. We can have something else. We have some real number. Let's make this one a float just for fun, okay? Okay. So we have a couple of numbers. All right. Let's go ahead and output these. Oops. All right. Yay, it compiled. So what's going to happen when we run this? What is this thing going to output right here for pi? This whole number here. What's real going to output? The whole number. Is that what y'all think? Is that a pretty reasonable assumption? That's what we've seen so far, right? So let's see what happens now. Wait a minute. Is that right? What happened? It sort of cut off some of the numbers, didn't it? So if we look at pi, here's what we had. 3.114159265, and this one did 3.14159. For the other number, we had 127,382.926, right? And all it did is 127,383, right? This was 2.9, and it rounded it up to 3, apparently. Is this sort of confusing? Yes? Nope. Float, actually, his question was float too small? Like, is there enough bits to hold this number? The answer is it may not be, but that's not why we're seeing this problem. I don't want to mislead you. Yes? Nope, we can take the IO manip out and we will get exactly the same results. I put IO manip in there so we can fix this because we're going to use it to fix this. So, okay. So let me just put IO manip back. So I just took IO manip out quickly, compiled, and ran it again to show you that IO manip didn't cause the problem. All right, here is the deal. In cout, when you output, in general, but not always, in general, cout will produce 6 digits of output. 6 digits of output. What's baffling about this is that when you and I think about 6 digits of output, we think 6 digits past the decimal place. What cout is doing is it is showing you 6 digits of the number. And the rest, it's sort of rounding. Okay. Now, I say in general because we can do stuff like make this number a little bit bigger. What happens if we make this float 7 digits? it switches to scientific notation, it still gives you 6 digits. All right? So, cout by itself will show you 6 digits of the number. That is 6 numbers, not including the decimal point. If the number is too big, it's bigger than six places, like it's bigger than, what is that, 1,000,000, it will put it into floating point notation. How many of y'all like looking at numbers this way? Nobody raise their hand. How many of y'all like looking at numbers this way? Nobody. Nobody likes looking at numbers this way, and I agree with you. This is a stupid behavior. It's bad. You know what would be good behavior? If we could fix it, right? So, how many of y'all want to see how to fix this? Yes, you will need this for your project because we'll be doing floating point numbers. Okay, so what we're going to do is we're going to use something called set precision. And set precision is a little command that you stuff into cout. You don't need an end line. And you tell it how many digits you want to see. So let's say we want to tell it we would like to see 10 digits. What's going to happen when we compile and run this now? Any predictions? Yeah. It will display 10 digits of the number. By digits, we actually mean individual characters, right? 10, not 10 digits like you think of math digits past the decimal, but literally 10 things, not including the decimal point. 1, 2, 3, 4, 5, 6, 7, 8, 9. For pi, we only had 9 digits, so we showed those. For the other one, it showed us 10 digits. 1, 1, 3, 4, right, 1, 1, 2, 73, 8, 7, 5. 8, 7, 5, that's interesting. Well, check this out. It's showing us 875 here, but our number up here was 926. What is going on with that? All right, so before we talk about this, I want to make sure we understand, right? By default, you get 6 digits. 6 digits are actually characters, not including a decimal point. If it's over 6, it goes to scientific notation. We don't like that. Set precision tells us to use more digits. It doesn't change the number of things shown after the decimal point. Okay. Everybody good with that? Now, we saw when we did set precision, no, seriously, is everybody good with that? I should have run off. Yes? It's crazy, right? How many of y'all think this is crazy? This isn't the way people think. Yes, when we talk about set precision doesn't say how many decimals you show. It says how many digits of the number you show, not including the decimal point, either on the right or left, all put together. All right? That is not human-friendly behavior. This is not how we think about numbers. But it's what cout does by default. Everybody on board with that? Yeah?
Why can't we just put set precision to like a large number?
We can put set precision to a large number. We can. It's fine. But I'm going to show you a different way to do it. Okay? I like showing you the ways that things break, because if I show you the way that things work and you do them wrong and they break, you'll be confused. If I show you the way that they break first and then I show you the right way, then when they break, you go, oh, I know why it's broken because I've already seen that. Does that make sense? So there's method in me showing you all the insane stuff first. Yes?
Once you put set precision once, will it be like that for the rest of the code unless you change it?
Exactly. So thank you for pointing that out. I forgot to say that. Remember we saw set width before? Set width only affected the single next thing that came along. Right? Only the next thing that came along. Set precision, once you stick it into cout using the angle brackets, affects everything from that point on down until you change set precision again, should you choose to do so. Which we will not in general. We will use this to fix output and leave it like that. Okay. All right. Yeah? Yep. This one set precision right here will affect every cout from then on. All the way on. It's like flipping a switch. Once the switch is on, it'll keep doing it. Set width is not like that. Every single thing you want to set to a particular width, you have to put it right before that. Who's happy? Good. I like it when I have happy students. Makes me happy. I'm not. I'm actually generally pretty grumpy. So, all right. Not that you would care. So I'll stop talking, except about this stuff. Okay. So here we are, right? Now, what happened when we output real? It has this weird number there, 875. Like, why is it 875? You've programmed before, haven't you? All right. What do you want to guess? That is 7/8. It rounded it to 7/8. Why did it round it? So here's the deal. I'm just going to show you this really quickly. You don't have to know this, okay? So if we have powers of 2, right? Are all these powers of 2? Do you remember when we talked about binary numbers? So we would have something like this would be a 1, this would be a 0, this would be a 1, this would be a 0. We'd have a 1 for 4, 1 for that, 1 for that. This isn't actually matching our real number, but this is how binary numbers worked, right? Everybody remember that? So the way you can think about floating point numbers is that once you get down here, you have 1/2, 1/4, 1/8, 1/16, 1/32. So if 2 to the 1 is 1, 2 to the minus 1 is 1/2, and then 1/4, and then an 1/8. So what happens when we're dealing with these floating point numbers like this, we have to make it up out of a fraction of sums, of a sum of fractions, excuse me. So we have to take all these little pieces and add them together in such a way that we get our floating point number. All right. How big a number is this over here? It's like over 1 million, right? So we need a lot of these positive powers of 2 that go all the way out to 1 million. And then we need some fractional part too. What type is this? Real is a what type? Float. Float doesn't use very many bits to represent the floating point number. It only uses a small number. So what's happening here is we're seeing a couple of things. We're seeing, first of all, that set precision isn't helping us because it's not showing us enough thing. Let's try making set precision larger and see what happens. Actually, not sure what's going to happen. So, all right, we made it much larger, and we still get 0.875, even though we told it to carry around 15 digits, which should be enough to show a lot of that, right? What's happening is because we have float there, on the fractional side, it's saying, okay, well, I'm trying to get as close as I can to 0.2960901. The way I'm going to do that is I'm going to put one thing at 1/2, and I'll put one thing at 1/4, and I'll put one thing at 1/8, and then after that, it's probably out of places it can put digits, because we used all the other bits in that box to represent this 1 million number. It just doesn't have enough bits to represent the fraction. Everybody kind of understand what I'm saying here? Yeah? Everybody see the problem here, right? The computer is using these fractions to add up to get as close as it can to this number, and it can't do a very good job. And this is what's known, it's a problem, right? It's a common problem in computing that floating point numbers have these inaccuracies. And they have these inaccuracies because you're trying to get close to a fraction by adding these little pieces together. Yeah? All right, so the question is, what's the last fractional power you can use? And the answer, no, this one right here is the last fractional power that this particular number is using, because 1/2 plus 1/4 plus 1/8 equals 0.875, if I'm not mistaken, right? And so that's why we're seeing 0.875. If we were extending this out so we had a lot more fractions, it would be a lot more accurate. And in fact, how about we do that? Who wants to see that happen? Yay, me too, because it's crazy. So if we change this to a double has twice the number of bits for representing the number. It can represent a lot more fractions. And when we compile this and run it, we will see now it doesn't say 0.875 anymore. It actually has the number that we want. And the reason is we gave it like 32 more ones and zeros that it can use for coming up with smaller and smaller fractions, and it adds all those up to get close to our number. Yes, sir? Float is too small. You're absolutely right. So I wasn't trying to shut you off before, but we were seeing something weird. Or did I misspeak? The problem was not because of the box, but because float was too small. Okay. So if I said otherwise earlier, I apologize. You were right. Okay. Everybody understand this? Floating point numbers in computer science are dangerous. They are dangerous. It is possible for you to do a calculation that works out exactly to some number, and then if you compare it to that number with equal signs, it will not match. And the reason it will not match is instead of 4 being equal to 4, it'll be equal to 4.00000000001. And the computer looks, and the computer will go, is 4 equal to 4.0000001? Nope, sure isn't. It's different. So you have to be careful when using floating point numbers. Okay? Always use at least double, because float is too small. Everybody good with that? And if you ever see rounding error in computers, this is where it comes from. When I was in graduate school, which admittedly was quite a while ago, I took an entire semester class that was essentially on numerical analysis, which is how do you do numerical analysis and simulations with floating point numbers in a computer so that you know how accurate your results are. You can spend a whole semester just dealing with this problem. You don't have to if you don't want to, but it's the problem. Okay. Everybody good? All right, 1 minute break in place. Stand up really fast. All right, welcome back. By the way, I want to say one thing. I've shown you here how floating point numbers work. It's totally a lie. They don't work like this, okay? But conceptually, this is how they work. Computer geeks have optimized this like so crazy that it doesn't really quite work like this. It's much more complicated. But conceptually, this is what's going on, and this is why we see weird results sometimes if you don't use enough digits, okay? All right, are you okay with me lying to you about that? Because literally it would take like 2 days just to explain how numbers are stored in memory as floating point, but that is sort of what works. All right, so here we are. We now have our program that we can run, and we print all this stuff out, and we're happy, right? Except for one thing. How often do we really have to deal with like all of these numbers behind the decimal place? Not often, right? How many decimal places do you normally deal with? Like 2, maybe 3, right? Depends what you're doing. Like day-to-day use, you'll use 2. If you're a gas station, you use 3, so you can have that annoying little like tenth of a fraction of a penny thing that makes it look right. So you don't really need that many decimal places. So let's get rid of some of these decimal places. So set precision is obviously too high. Let's treat these as dollars and cents. We want 2 decimals after it. So obviously all we have to do is change set precision to 2, and we're good, right? What do you mean no? Let's see what happens. If I run it, oh, you're right. That's bad, right? Pi is not 3.1, and that other number is not 1.1 times 10 to the 6th. Set precision 2 doesn't do us any good to show decimals. What we would like is we would like set precision to work the way that we think about working. What we would like is we'd like set precision, instead of showing some number of digits that's sort of arbitrary, to actually tell us how many decimals it's going to show. Wouldn't that be great? Okay, so let's fix set precision to make it work the way we want it to work, which is to show 2 decimals. And there is one magic command to do this. That's it. Cout fixed. When you use iomanip and you put fixed into cout, and then you call set precision, it changes how set precision works. Okay? Set precision at that point, instead of showing that many digits, regardless of whether there's a decimal in there or not, now switches to showing that many digits after the decimal. After the decimal. So if we run this now, what do you think we're going to see? 3.14 and 0.9. 9, 2, or 3. Let's see what happens, okay? It might, 0.93, it rounded up in this case, okay? So we get 2 digits, 3.14 and 1127382.93. In that case, it rounded. Yes, sir? Okay, so the question is, when you're doing calculations, isn't it just best to use as many places as the computer can fit? The answer is maybe, right? So here's the problem. When you go from a float to a double, your number takes up twice as much space. When you go from a double to a long double, it takes up twice as much space again. Your computer has a limited amount of memory. In a program like this, where we only have like 2 numbers, we have enough memory to do whatever we want. But if you're doing a real calculation and you're dealing with lots and lots of numbers, you may not have enough memory to store every single one if you use a long double. Does that make sense? So you sort of have to know how to trade off. For this class, we're probably never going to reach the limit of RAM, the limit of memory we hear. But I want to teach you now so that later you sort of can understand the trade-offs, right? Does that make sense? For this class and for most of the stuff you're going to do, double is probably good enough. So I recommend double. All right, so this is nice, except now these things don't line up, do they? What if these are really dollar values? Wouldn't we want them to print out in some way that like the decimals aligned nicely? How would we do that? Somebody said set width. Absolutely. Here. Okay, so we can use set width for that. How do I use set width in this case? Set width. I don't know. How big should we make set width? Pardon? Larger than the largest amount of digits. So this one's going to have like 6 digits. I'm just going to put like 12 in here. So, right? And what this is going to do is it's going to pad everything out so that it fits in 12 digits. And let's see if that's actually big enough. There we go. Everything lined up nicely. Okay. Everybody good? Yeah. If one had 3 places and the other had 2, yes, you'd have to do some stuff to figure out how long it is. You know what I would do? Here's what I would do. If one had 3 decimals and the other had 2, set precision 3. Woohoo! Wait, that doesn't answer your question. Here, let me give you a real one. Double, fries. How much do fries cost? $2.40. Okay? So now, is that too much for fries? It's a really big fries. It's like a Five Guys fries. Okay, it's like 2,000 calories worth of fries. Guess where I'm going for dinner tonight, by the way. Okay. my wife's out of town, so I gotta feed the kids. Oops. Oh, wait, who yelled that out? All right. All right. Oh man. All right, I want you to take a class in public typing and then try this. It's not easy. All right, here we go. So now it gives us an extra 0. So this formatting stuff can get really annoying and picky and complex. I'm not going to be that picky for you in this semester. Yeah, Roberto. Uh-huh. No, set width you have to use over and over again. If we took out the set width, we would see that one of the things wouldn't be aligned. So, is that what you're saying? So fixed and set precision work forever. Set width you have to do every single time. Now, is that annoying? Is that what you're asking me? And you wish you didn't have to do that? I wish that too. That if I got the genie out of the bottle, that would not be one of my first 200 wishes, but it might come shortly after that. So, yeah, you can copy and paste. Like the editor you're using right now, Nano, honestly, it's like dinky and sucky, right? I just can't give you the super powerful editor first because your head would explode. There'd be too much to learn. Over the course of the semester, as you go along, when you get tired of working with Nano, you can try a better editor. But just for this, I'm trying to give you the minimal amount of stuff to learn at once. Make sense? So it'd be like, if I was trying to teach you to like deliver pizzas and I put you in an airplane the first time because there's like crazy controls everywhere, I wouldn't. I would give you a little red wagon to pull behind you so that you had the least amount of stuff to learn. So that's what we're doing here. And I know it kind of sucks, and if you have the capacity to learn more, I'm happy to help you. But okay, everybody good with this? Number formatting? You will need this for the project, so that's what we're talking about right now. Whew. All right, let's see. So if we do output, we also have to do something else. Input. Let's do some input. All right, so here we are. What do we want to input into? Let's say we have an integer x, and we set it equal to 0 initially. Why do we do that? So we don't just have something random in there. We don't know what it is. Even though we know we're going to do input, we initialize stuff, okay? And we'll do another char D. That's too confusing, Z, okay. All right, so what is our algorithm here? Yeah? Yep. The question was, if you don't initialize a character, do you get weird crap coming out of that? The answer is yes. There is some random number left in there, and it just says, this thing's a character, and I will look at those numbers and try and make it into a character, regardless of what it is. Even if it used to be an integer or a double before, you will get something random and arbitrary. So it will look at that bit and reinterpret it that way. Okay, so what does our algorithm do here? Pardon? Nothing, but it does some stuff. What does it do? Uh-huh. That's right. It says we create a box named X. It's an integer. There's a 0 in it. Box named Y. Integer. There's 0 in it. A character named C, a box named C that holds a character that's a space. A box named D that holds a character that's C. Not very much. It's a boring program. So let's do some input. What is our input? Our input is Cn. The angle brackets go the other way. Okay, the angle brackets go the other way. Whereas if you think of these little angle brackets as a funnel, before we were shoving stuff through the funnel to the screen. Now stuff is coming from the keyboard, which is CN, and getting stuffed into a variable. So let's put some stuff into X, and then we'll end the line. Okay, how's that look? Yeah. Okay, if we did this, X equals 12, like that, this is actually assignment. And what's going to happen is when our program gets compiled, this 12 is going to be a fixed value that's in there forever and ever, and we can't take it out. CN is going to stop and say, I need a new value for X. And the way I'm going to get it is I'm going to wait for the user to pound on the keyboard and tell me what to put in there. Does that make sense between the two? Yeah. We're going to be using this a lot during the course of the semester. You'll use this for the project and every other project and stuff for the rest of your computer science career, however long it may be. Okay? Yeah? Oh, it's not, is it? Well, let's run it and look and see what happens. That's a very good point. So, all right. Oh, no. Something went horribly wrong. Oh, my God. Ooh, that's bad. All right. Do you remember I told you that the compiler on occasion would be incredibly unfriendly to you? Do you remember when I said that? This is one of those occasions, okay? Here's what happened. I ran the compiler. It gave one error message, and then it just went nuts and dumped stuff everywhere. When you get this problem, here's what you do. You only look at the very first thing. Don't worry about anything else. It can be, I mean, honestly, I've had this go on for like a minute where it's just like, and I'm like, you know, and it's just horrible. All you have to do is look at the first thing. Got it? So what went wrong here? Error referenced overloaded function, CN angle X, oh, ENDL. You know what? Yeah? ENDL does not work for CN. You cannot use ENDL with CN. You cannot. What will happen when you do? The compiler will barf all over your shoes, right? It will. It'll dump all this stuff out. ENDL is only for cout. Only. Okay? So, this is a common mistake. Everybody makes it at some time. I'm making it now so that when it happens to you, you'll remember. Okay? So personally, I'm somebody who learns by their mistakes, so I make a lot of them, and I try to learn from them, like, if not on the first time, at least on the 12th or 13th or 20th, okay? So it's natural to make mistakes, it's natural to do stuff like that, and so, okay. So now, let's clear the screen, we'll try and compile it again. Now the compiler's happy, it doesn't yell at us, we're fine. So let's run this. What's it doing? How do we know that? I guess the color is a different color. I hadn't noticed that. Cursor, yeah. All right, it would if it finished. So something's happening. It's hanging. It's hanging because if we look at our algorithm, we do some assignment, and then we do input, and the computer is waiting for us giant, slow, monkey people thing to type something in, okay? If I type something in and I hit enter, it will finish and it will be happy. One of the things about doing input is you should tell the user what you were expecting, because otherwise this happens. And it's really hard to tell if your program's even working, right? I mean, you have no idea what it's doing. It could be, you know, running malware that's infecting the entire internet and it's just too busy to talk to you right now. So, or it could be waiting for you to enter a number, something like that. Okay. So, let's try this. All right, what's going to happen now when we compile this and run it? Yep. What int would you like to put in there? 5? It's a pretty conventional choice. All right. So I'll tell you, one of the things about input is I put that end of line there just to show you. I kind of don't like input like this. What I normally do when I'm doing input is I put a colon and leave a space. And that way, when we compile it and we run it, you can actually see that the integer goes right on that line. Okay? Yeah. Okay, we could put 5.3, but let's do that in just a sec, okay? So we got an int, and now let's output something. Cout. All right. Oops. Output x. I meant to type x there. So now we have a nice little program. The program is a pretty simple algorithm. You run it. It asks you for an integer. What's your favorite integer? 7. Okay. And it puts that out. Now, your question is, what happens if you put a decimal number? Will it? Oh, wait, I didn't have to compile. We'll just run it again. All right, shout out. What number would you like, sir? 5.3. Ah, you got 5. It's not an int. All right. Something horrible just happened. Horrible, horrible, but you haven't seen it yet. So let me show you how horrible it is. And then we'll talk about next time how to fix it. All right, so let's do this. Enter another int, cin into y, cout x, cout y. All right, so we're going to enter an int, enter another int. Let's just make sure this works. We'll compile it. We'll run it. Somebody name me an int. 19, thank you for that adventurous choice in integers. Anyone else? 28. Woo, that was exciting. All right, so that worked. Question?
How does the computer know to go back to like another line after sin?
Because what's in it, what? So after I enter 9, why does it go? After I enter the 19, does it go to the next line? Because I hit the return key after 19. That's why it sort of happens. Now let's use your number of 5.3. Okay, is that what you want? We'll run it again. We'll enter an int 5.3, and what's going to happen after I hit enter? Yeah. And what else is going to happen? What? Horrible. Something very horrible happened. Here's the problem. Cin, when it reads numbers, is greedy. It's greedy. So let me run this one more time. 127.365.82. Oh, shoot. What cin is going to do when you type something is it's going to say, I am looking for an int. The first thing it's looking for is an int, and it will find the biggest int that it can. Could 1 be part of an int? Okay. How about if we add a 2 to that? Would that also be an int? And a 3? Or and a 7, and a 3, and a 6, and a 1? That's a pretty big int, but we're good, right? And then a point? No, there's no point in it. So what cin's going to do, it's going to say, aha, I will take this whole thing right here, 127.361, and I will stuff that into the variable named x, right? Because we did cin into x, so it does 127, whatever, stuffs it into x. And it goes, okay, now I have to enter another x, it outputs it, and it goes cin into y. Okay? It's going to put something into y. What is the next thing that the user typed after this integer? A point. Is a point an integer? No, it is not. So what does cin do? Cin gives up and goes home. It says, if you are going to give me something that I cannot process, I'm done, screw you, goodbye. And it stops processing input. Completely. It completely stops processing input. It's just done. And what happens is any cin after that, after you have this problem, is ignored. It doesn't happen. Okay? For the whole program. Let me give you a demonstration. So here is project 1. Here's all the stuff I've been working over this weekend. This is the program that you're going to be writing for next week. So let's enter a subject ID number. Thank you. In age, how old are they? They're X. Oh my God. What happened is once I entered X, every other one of these inputs that it was waiting for is done. It says, I'm done. You gave me something I don't like. I'm going home. Screw you. Have a nice day. Okay? That's literally what it does. All right. See you next time. What? Why are you all looking at me like that? I'm not going to, I mean, we can talk about how to fix it, and we will, but this is what happens. If you get the wrong type, it goes awry. And we'll talk about this more next time. Have a good Tuesday.